Hello, everyone. Thank you for joining me today for today's webinar. So I'm actually speaking to you guys from Schaan in Liechtenstein, where the headquarters of Ivoclar Vivadent is based. And today I'm going to talk to you about light polymerization and how each of those factors that you need to actually take into consideration and how it's going to influence your daily practice. But before I go on, I'd like to first give you some housekeeping rules. So what you'll find is that you're all automatically muted. However, you are, I would like you guys to ask any questions that you have, and hopefully we'll address them at the end of the session today. Now, in order to do that, if you look onto your GoToWebinar software, you should find an orange arrow here. So I'm just getting that laser point there. And if you click on this, it should drop down and you'll find questions. And if you drop your question there, I will be able to see them and we'll try and address as many of your questions or any doubts that you have by the end of this session. Okay, right, let's move on. Brief introduction. So my name is Dr. Kopikrishna Thirunelakandan. You can call me Kopi for short. I'm also a dentist like yourselves, and I graduated over 10 years ago, and I did my postgraduate training at the UCL Eastman Dental Institute in London. That's where I was born and brought up. And so I worked in the dental clinics or in private practice in the UK before I moved to Switzerland. So when I moved to Switzerland, then I changed my position, and now I'm a global education clinical manager at Ivoclar Vivadent in Schaan. So I'm just crossing the border. So because we can't live in Liechtenstein, but I live in Switzerland, we can cross the border. And that's where I do a lot of trainings, workshops, travel around the world to give training to other colleagues like yourselves. However, right now we can't, so that's why we're now offering webinars at the moment for free, as you can see. But hopefully we'll get to see each other at some point in person. I'm also still practicing as a dentist. We have an internal clinic at the R&D department, so our research and development department, where we also treat our patients in the local area, so that we're, also being able to keep our hands also wet in dentistry. Right, now moving on. What I'm going to do is I'm going to divide this webinar into 3 parts. So I'm going to give you like a background knowledge to sort of bring you all to one level. Of course, maybe it's a little bit of revision. Maybe there's some things that you probably don't are aware of. So try to bring some foundation. Then I'm going to introduce you next to what are the common mistakes that we find in practice, what people aren't aware of. Not to say that they do it on purpose, but like sometimes there are small things that make a difference in your dentistry. And then how to rectify it, so with successful curing. And I will give you some tips and tricks. Okay, right. Now, here's a study that I wanted to share with you. So how important light polymerization is and how adequate it needs to be, because unfortunately, while the chemistry of the materials and equipments and clinical techniques have advanced, constantly advanced over time, clinicians often undervalue the importance of light polymerization, because that light, they'll use really great materials. There's so many great materials out in the market. There's great adhesives, and so on, but then they just skip that point where they realize, okay, they just light cure it and they don't light cure it appropriately. And that's one of the factors where it affects the longevity of your restoration. And so there's also a study done where they found that inadequate light curing can lead to compromised physical properties, okay? And another study by Ferracane, you probably already know, from '97, he said, you need adequate light polymerization to actually have a good degree of conversion of your polymers, and that whole also, so it was confirmed from the previous study that I showed you in the slide, where it will give you very high physical properties and making sure that there is no marginal breakdown of your restorations. So just make sure you're aware and understand the proper use and the limitation of your light cures as well, because there are different light cures in the market and some are capable of doing some things and some are not. So you need to be able to understand the equipment that you're using in your practice too. Right, so complete light curing. The problem is here is that, as I said, light curing is often taken for granted. So, it's well accepted fact that, when you don't cure your resin materials, anything with like composites to your adhesive, you're going to have like compromised quality of your restorations. And what it can lead to is hypersensitivity. If the adhesive, for example, is not fully cured at the bottom, you can have marginal gaps, increased abrasion. So if the composite is not fully cured, then they're prone to wear and reduced life cycle, because you probably end up needing to redo the composite or even your indirect restorations. So that can lead to debonding, and of course, there's talks of toxicity of uncured monomers, especially when they're so close to the pulp. Now, what are the requirements that you need to be asking yourself? So, as clinicians, we need to know, okay, especially when you go to your sales rep, or if you're someone who's buying the light cure, or your boss or your practice manager is buying the light cure, the questions that need to be asked are some of these. What light intensity is your light cure able to produce? What are the spectral emission range? Which I'll go into a little bit more detail. But this is one of the questions you need to be able to ask, because there are so many different materials in the market, and your light cure needs to be able to be, let's say, versatile in order to polymerize all these different types of materials. What are the ideal techniques in trying to light cure? You need to know how long you want to expose your material for. So can you be more efficient by light curing for a shorter period? If you're lighting for a shorter period, are you getting all the energy that's required? And of course, the quality criteria. So you need to be looking at what your light cure is able to offer. Is it constantly producing the intensity that you think you're buying at? Or how can you make sure that it's producing that kind of intensity? Constantly. So, over time, we're talking about equipments that can wear down over years. So you need to be sure what you bought in terms of light intensity, maybe say 2 years down the line, that is still producing the same intensity or sufficient intensity in order to still polymerize your material. Now, because this is actually quite an interactive webinar, of course, I've got you all silenced. However, you are still going to be taking part in some, let's say, polls or survey. So I'm going to actually address a question to you guys already. So I want you guys involved. And the first question is to you: which of the following below is most important feature to you? So when you've got a light cure or you want to polymerize something, what is important to you? Is it light intensity? Do you prefer to have short curing times? Do you want something that can cure all types of composites? Or would you like a feedback from your light curing device to tell you that you're curing accurately or appropriately? Or E, all of the above. So let's get you involved. So let me launch that poll and let me know what you think. Give you a few seconds. Great, so some of you guys are getting involved already. Like that. Okay, right. Thank you for taking part. I'm just going to share the result. There we go, let's have a look. Can we see that? All right, so majority of you guys would like everything to be viewed in from, or you look at all the criteria. That's great. So some of you guys think about the light intensity. That's not wrong. Short curing times, of course, yeah, because we want to be quite efficient in our practice. We don't want to be curing for 40 seconds anymore like we used to with halogen lights, of course. All types of composites, great, yeah. However, yeah, it's great to see that that those 3 points are the main parts, but it's also quite a bonus to have if your light cure is also able to give you a feedback, but that I'll come to in a minute. So, right, let's move on. Now, in some of the surveys, they say a dentist requirement, they're asking, like you guys have voted, they wanted a high light intensity so that it's able to cure through higher depths of composites, so in their indirect or through some ceramics. Shorter curing times because they don't want to spend too long, and of course making sure that they're fully curing their materials. Now, let's go on to the background now. Again, I'm just going to get you involved one more time because I want to know, what curing light do you guys use in practice? Because it'd be interesting to know what you guys are using. So I'm just going to launch this poll. Just let me know what you guys are using. Do you know if you're using a halogen lamp still? Are you guys using a monowave LED light cure? Or are you using a polywave LED light cure? That means, you know, with different LED lights in the light cure. Be interesting to know what you guys are using nowadays. Okay, right. Thanks for taking part, everyone. I'm just going to share. So let's have a look. Yeah, so it seems to be neck and neck between the two. Let me just try and show that. Sorry, bear with me. Yeah, there we go. So it's a bit neck and neck. So some of you guys are still using halogen lamps, okay? Half of you guys are using a monowave, and almost half of you are using a polywave. So yeah, so some of you guys sort of moving on to what we call the third generation LED lights there. What I'm going to do, I'm just going to hide. I'm just going to talk to you a little bit about the new LEDs. Let's see. Right, so light curing units. So historically, in order for us to be able, when resins were sort of discovered, they needed a certain energy to be able to initiate the polymerization reaction. And what they came up with was the quartz tungsten halogen, which is obviously for short called halogen light. Here's the Australis 7. Well, at that time it was called Vivadent. They produced this light cure, which actually now isn't used so much in the market these days, of course. However, back then, you know, we're dealing with a quartz bulb. So it has a tungsten filament that actually irradiates both UV light and white light. And because we don't really need the UV light, but we don't need the whole spectrum of the white light, we just need the blue range. So what it is that from the filament, it shoots out these wavelengths, and then there is a filter. The filter actually filters out all the wavelengths except the blue light. And that's how we were able to generate the blue light from the halogen light cures. However, with this, because of the filter, it loses a lot of its energy, because what happens is that the filter can pick up dust. The filter can also have cracks or scratches and so on. So it actually diminished the intensity, but at the same time, over 90% of the energy is actually heat, and only 10% was the actual blue light that we needed. So a lot of energy was lost, but at the same time, when we're looking at the intensity and the power, it wasn't strong enough to light cure all types of composites for a longer period. So that's why we needed about 40 seconds to polymerize 2 millimeters of composite. And the other thing is that when we have, even though it actually has a broad spectrum, so I think it ranged from about 390 nanometers to about 500 nanometers. So it was quite a broad range, but it just didn't have enough power. There's the plasma arc curing light, and then you've got the modern LEDs. The modern LEDs, of course, nowadays is where they just have blue LEDs that emitted the blue spectrum of the visible light, and these are have long lifespan, without deterioration of the power. But the earlier versions, so they don't need filters, but the earlier versions actually didn't have enough power back then. But of course, over generations, they developed them in order to be able to meet the demands and the requirements that we need for today's dentistry. And the other great thing is that they actually don't take so much space in the clinic or on the desk. They don't, the power, it can be either wired or they can be battery powered. So, and they don't generate so much heat like the tungsten halogen lights. Yeah. So we're going to focus more on these types. So moving on. Over the years, there were generations of different LEDs, and Ivoclar, they've had the first generation blue phase in 2004. And this was when, as I mentioned, only had a monowave and the intensity wasn't strong enough at that time in order to be able to cure composites at deeper levels, and it needed longer curing times. So then from there, the second generation was developed with a very similar style, a similar design. However, the intensity was a lot higher, so higher power, so people were able to actually cure and reduce the curing times. But they still had their limitations. They were narrow in terms of the spectrum, so it wasn't like the halogen lights, which had a broader spectrum. They were a lot more narrower. So you're talking, you know, about 420 to about 480. So it's very narrow. So only specific types of photoinitiators were able to be initiated, like camphorquinon, for example. However, when there were more composite or different types of composites in the market that came out, they needed a broader spectrum. Hence came the third generation. The third generation has a broader spectrum because of an extra LED light that's involved, which I'll talk to you guys in a bit. And then of the fourth generation is what's now called the Blue Phase Power Cure, or the Blue Phase G4, where they're able to give you a feedback mechanism. So it has a feedback mechanism to tell you if you're curing accurately as well. So it's all progressed over what is demanded by the dentists. So light is an electromagnetic wave, and from there we only need the blue light. So we're only talking about 380 to 500 nanometers, and that's what our blue light is able to emit, and that's what we need in order to initiate the polymerization reaction. And then when we're talking about photoinitiators, so we have the camphorquinon. This is the classic one, the first one that was developed. And how it works is that, so for the polymerization reaction to happen, you receive an electromagnetic energy from the light. And so from there, it comes in the form of photons. And from there, it releases free radicals. And this free radical starts actually releasing energy and tries to look for other, let's say, electrons that it can actually bind with in the material. And I'll go on to that for a second. So here we have, for example, a methacrylate-based monomer, which has a carbon double bond. So a carbon double bond in the molecule here. And when we have an energy from a free radical, which has high energy of electron, or which has electron on its outer shell, it's actually looking for an electron-rich area, hence the carbon double bond in the methacrylate. And what happens is the free radical actually starts clashes with the double bond and forms an actual carbon covalent bond with one of the carbons. So then it forms a bond there, and then what happens is, if the one electron from the carbon double bond becomes free, so leaving behind a single covalent bond, and then it allows the electron from here to go onto the outer shell, and then that forms itself a new radical, and then that goes into the medium. And then it's like a chain reaction. So, you know, it's like one free radical is released, it hits an electron-rich area, forms a bond there, releases another electron, and then so on. And the only time when it actually stops is when there is no more concentration of free monomers to polymerize, or because the material becomes a bit too solid so that the actual free radicals cannot move, or when two free radicals bind together, and then the polymerization reaction actually ends. Right. So this is Professor Krejci, and he suggested that we need a minimum of about 400 milliwatts per centimeter squared of light intensity in order to cure any resin-based material, especially like composites. But with 400, that's the bare minimum, because with 400, you still need about 40 seconds to cure, and I will come to that calculation in a minute, but that's what he recommended. However, when we are dealing with indirect restorations, or we're dealing with deeper cavities, deeper fillings, you can't guarantee that you'll get that 400 milliwatts per centimeter squared of intensity further down into the deeper areas. And that's why, we recommend at least 1000 milliwatts per centimeter squared, and that's what you find in a lot of the light cures around the market. And that's going to give you enough power or intensity to polymerize the material. Now, we need to be sure that we know the difference between light power and light intensity. It's more or less like, let's just say, this is like light power is like your force, and then light intensity is the pressure, because power and intensity is completely different. You can increase the power but not get the same intensity. And we want to try and avoid needing too much power, and we can adjust the intensity because of how wide your light guide is. So if you have the same power but have a narrower light guide, you're going to get more light intensity. So you can control it like that rather than using more power from your light. And that's what I mean here. So when you've got a parallel walled light probe that's about 10 millimeters produced, and then you've got one that's a lot smaller, you're going to find that the smaller the diameter, the higher the intensity. And how is it calculated? So it is recommended, in order to, according to literature, we need about 12 joules per centimeter squared. And when we convert that, we need about between 10,000 to 16,000 milliwatts seconds per centimeter squared. So it's about 10,000 to 16,000, but we recommend let's take 16,000 so that we can get at least 80% of Knoop hardness. Knoop hardness is how hard the composite or a material is when pressure is applied, right? So, and if we have a light intensity, like Professor Krejci said, we need about 400 milliwatts per centimeter squared as a minimum. Then the resulting curing time is 40 seconds, okay? So if we increase it, we can half it. So if we increase it to 800, so we double the intensity, then we half the curing time to 20 seconds. And then of course, when you double it even further, you half the time. So that's how it really works, okay? Now, there are different photoinitiators in the dental world, as I already spoken about, camphorquinone, but because of its yellow color, it always used to give composites that yellow tinge, yeah? And we want to try and, so what companies did was produce composites that didn't have that yellow tinge, and then they came up with different photoinitiators that were able to use on bleach shade composites or lighter shade composites or adhesives. And then they have like PPD and Lucerin here. So these are absorbed at different wavelengths. So as you can see here, you've got camphorquinone absorbed around 390 to 510. These bleach shade photoinitiators are ranging from 380 to 430, and you're just thinking, okay, that's not a problem if I've got a broad spectrum. Yeah, with the halogens, it's not a problem, because with the halogens, because they've got such a wide spectrum here, it's going to initiate camphorquinone. And the same thing, it's going to initiate Lucerin. But remember, halogens don't produce high enough intensity, so you're going to be curing for a long time, for 40 seconds approximately, right? Now, if you had the monowave LEDs, or those like first and second generation LEDs, you're not going to have a problem trying to cure classic camphorquinone photoinitiator in your composites. But what if you had a bleach shade? Now look at this. So we're talking about what I mentioned. If I bring it back, 380 to 430, so we're talking like 380 to about 430 here, and your standard blue LED ranges around here. You're going to struggle to actually initiate it around there. It's kind of missing that part. So that's why you need an LED that's able to cure both. So it needs a broader spectrum, but at the same time having high intensity. And there was some papers released in the magazines where, you know, they said, you know, not all LEDs can cure all types of materials. So that's something you need to be aware of. Yeah, it works generally on camphorquinone, as I mentioned, but other types might not be initiated. So be careful about that. So hence why they came up with the 3rd generation LED. Now with the 3rd generation LED, you still have the blue LEDs here, right? So that's from this range, and it produces about 1,000 milliwatts per centimeter squared. And what they also added was a purple LED, okay? And that actually broadens the spectrum of the light. So it pushes it down to about 380, and that also produces about 200 milliwatts per centimeter squared. So that's why when you add it together, a light cure will have about 1,200 milliwatts per centimeter squared. That's what they say. And so with this, you're starting from about 380 to about 510, 530. You're going to find, if I show you the next slide, that with this broad spectrum, you're going to be able to initiate all different types of light cures in the market, all types of photo initiators in the market that are used for the composites. So yeah, you've got your Lucerne here, you got your camphorquinone here, and yeah, and if you've got this is the 2nd generation LED, so it's only going to initiate the camphorquinone, but not so much of the bleach shades with Lucerne, for example. But if you've got a broad spectrum, if I zoom in, you're going to find that it will initiate those bleach shades and your adhesives that you're using that has that, okay? So that's important. So yeah, just have a look, just make sure whatever light cure you're purchasing in the market from your sales rep, that it has a broad spectrum so that you can be open to any composite that you want to use in the market. You know, it doesn't particularly have to be one that has camphorquinone. You're able to use your bleach shades, which is becoming more and more common with patients wanting to have whiter teeth, and you're doing direct composite veneers and so on. You know, it's important to make sure that you've got the right equipment. Okay. Now that's the polywave versus the LED. How do you know which light you have or which type of LED you have? Well, if you get your anti-glare or UV shielding UV shield, and you take away the light guide, depends which one you've got, and you just turn it on, you should be able to see the difference. So this is the monowave. So it only has the blue light. So as you can see here, and the difference from the polywave is that the purple one looks a little bit duller there, as you can see. So that's how you can tell if it's a polywave or a monowave. And how significantly useful is it? So from this video, I'm going to show you, it shows a polywave versus a monowave. And as you can see from this bleach shade, so what they've done is they've just dropped some monomer down, and with the polywave, it light cures straight away. But with the monowave, it doesn't cure it at all or much. And so the monomer drips right the way down to the bottom. Right, so some studies actually showed with the polywave, it improved degree of conversion and the Knoop microhardness as well. So it showed that 3rd generation was the future for adhesive dentistry. Okay. Right, so common mistakes. Now you know the background. Now you want to actually address any problems, or you know, we might have the right equipment. Now you've maybe already got a polywave, but you want to be sure that you're using the equipment correctly. Okay, now I'm going to get you guys involved one more time. I'd like to ask you guys, who polymerizes the composite layers in your practice? Do you allow your dental assistant to do it, or do you do it yourself? Be interesting to know. Well, you guys are getting involved. That's great to see. All right, just going to close that now. Again, thank you for taking part, guys. I'm just going to launch the result again. So the majority of you guys are actually light curing yourselves, and some of you are allowing your dental assistant to do that. And I'm telling you, there is no right or wrong. It's as long as they're done in the correct way, and I will show you how and why. But that's great to know, because I personally like to cure it myself, because I think in terms of logistics, it's easier for me to just, you know, be sure I know where I'm light curing and how I want to light cure it. But if your dental assistant is well aware of how to do it, why not, you know? Right, so I'm just going to hide that now. And this is what I want to try and show you guys. You don't want to be doing this, whether it be you or your dental assistant. Be sure not to lose concentration. Just be aware of what you're light curing. So not just light curing in the area, but not the actual composite. What you want to be doing is doing what this dentist is doing, or dental assistant. Doesn't have to be anyone in particular, but they're actually focusing the light on what they want to light cure. So that's important. And why is that important? Because what you can find is that sometimes if the light probe could be about 5 millimeters away, or it's actually angled away, or that it's angled and completely away, what you'll find is that sometimes you'll find some areas that weren't completely fully cured, and that can lead to secondary caries, and that's an issue here, you know. And yeah, sure, we could be talking about the upper left 7 or a 2-7 DO, and you can't get the light probe stuck right behind the patient's 7, right? But you need to be able to find enough intensity that it's also able to cure that deep. But I will explain to you in a minute there. But what they found, the importance of angulation here, you know, a study done in University of Munich, where they found there was a correlation between how much of the light probe was angled away from the restoration, or in this case, like a sphere, and how much intensity was actually lost. So here they started with about just under 4,000 milliwatts per centimeter squared, and when they actually increased it to about 30 degrees, and this is without any distance, they lost about 1,000 milliwatts per centimeter squared. But now imagine when we combine angle and distance, yeah, so we're talking about 5 millimeters away, then they've already lost, well, let's say from just under 4,000 to about 1,000 to 300. And if we even talk about just the angulation, you know, from the distance here, so just under 4,000, and you know, we're losing around 1,000 again here. So, you know, if your light cure is only producing about 1,000 to 1,200 milliwatts per centimeter squared, you're almost going to be in the range where it's not enough to polymerize your composites. And you know, remember Professor Krejci recommended minimum 400 milliwatts per centimeter squared. So if you have 1,200, you're going to have a questionable situation here. So okay, then we have the curing depth challenge, because nowadays when we have bulk fill materials, when we're talking about bulk fill materials, or we're trying to talk about endo, resto types of restorations, you know, or cavities, you know, we're not talking about just 4 millimeters or 2 millimeters. You know, you might want to be trying to cure the base, you know, after you've done a root canal, or you've got a deep class 2 cavity. How do you know? Because you can't exactly just trim away more tooth structure just because you want to fit your light probe in there, right? So you need to be able to know that wherever the light probe stops, that you're able to cure it. So here, look, for example, the distance from the light probe down to the base of the class 2 is 6.6 millimeters. And then imagine if you're not really focusing and you pull away a little bit of distance, then you've lost even more intensity because of that distance. And that could be quite vital. Okay, and then Dr. Richard Price, who's done quite a lot of studies, and actually he's done a lot of peer-reviewed articles on light cure, and he actually has written or co-authored this popular book. I'm not sure if you guys used this in undergrad. I used this a lot. This was also one of our Bibles amongst many other famous books. And he actually wrote in the 7th edition of this book, he wrote the part with light polymerization. So for the light curing chapter, he actually wrote that part. And so he did a study on the light cures and the effect on how much intensity we lose over time and with different intensities. So he compared the Ivoclar Vivadent's power cure, so the blue phase power cure. He used the turbo mode, which produces about 2,000, so around 2,000 milliwatts per centimeter squared, and then the high mode, which is the standard ones which you find commonly in many light cures, which is around 1,000 to 1,500 milliwatts per centimeter squared. And what you can see is a considerable difference when you lose that intensity. See, when you pull away from the material, whatever you're trying to cure, you're going to lose quite a bit of distance. So here, this is like the starting point. You're working around 3,500 or 2,200 here, and just all the way down to, and we're talking about a centimeter away, which can happen. I've noticed some people do cure about a centimeter away, thinking it's more than enough to cure the composite or whatever they're trying to polymerize, and they've lost about 2,000 milliwatts per centimeter squared here from the starting point. And here, if you look at the standard mode, you're going from 1,300 to about 593. So, you're still within the range, but not all light cures are producing that amount. They might be plus or minus. So if they're starting off with maybe say 1,000, then are you going to be reaching that minimum requirement of 400? So this is something to be aware of. And that's what Dr. Richard Price was trying to say. There's an importance on how you're concentrating that light. And then, of course, what's also very important when we're talking about concentrating the light, we need to be sure that your light cure is actually producing a homogeneous light distribution, because there are some lights that actually have different concentration of intensity. So because it depends on how the LED is distributing the light as well, how the light is delivered to the end tip of the light probe. Yeah, and what they found, and this is also from Dr. Richard Price, he found that some light cures have high areas of intensity and some areas where it's very low and wasn't producing enough intensity. So, and then why is that clinically significant? Well, if you've got high points here and you superimpose it onto a tooth, and say, for example, you're trying to cure a premolar in one shot with a MOD cavity, okay, look at some areas that are going to probably get sufficient intensity or sufficient amount of intensity to cure the composite, but then there's going to be areas of low intensity. And remember what I said about distance. So we're probably talking about 6 millimeter depth here on the proximal areas. And if you're not getting the intensity that you need anyway, because it's not homogeneous in terms of light distribution, then you cannot guarantee that you're getting the minimum requirement down these boxes here. But you're probably going to be able to do it in the middle here on the occlusal part, but in the proximal areas, it's going to be questionable. So that's also very important to address. So that's why if you have a light probe that actually produces homogeneous, then you don't need to worry about that. And also, then you don't need to multi-cure. You don't need to, especially in an MOD, we also need to think about pulp temperature, okay? So you don't want to be doing multiple curing. If you want to be efficient in your practice and you want to not spend too long light curing just to make sure everything is cured, then, that also helps. Okay, and the other thing is curing times. How long do you cure? And, the other thing that it's quite confusing as to what you can cure and what you can't cure and how long you can cure and so on. And in some composites they say, okay, if it's enamel and it's at 2 millimeter increments, then you cure it for 20 seconds if you're using halogen, or if you're using an LED which produces about 1,000, 2,000, then it's 10 seconds. However, if it's dentine, it's a little bit different. You need more curing time. And how can you measure, between 2 millimeter and 1.5 millimeter unless you have one of those perio probes, right? Same thing again here, curing times depending on different increment depths and different shades. So it's all very confusing, and it's always nice to not always refer to your instruction for use to know, okay, I'm using so-and-so and this is how much millimeter. This is also not time efficient in the practice. So it's also quite good to have curing times that are uniform. With the Tetric Evoceram, whether it be enamel or whether it be dentine, they're all 10 seconds if you've got a light cure that's producing around 1,000 milliwatts per centimeter squared. So just quickly referring back to the error sources that can reduce the longevity of your restorations. There were some studies done here where they've actually talked about the physical properties and the degree of conversion. So there's some studies here if you want to take photos of this. These are really good studies. And then another study here which actually talked about the degree of discoloration and how clinicians aren't aware of how important the polymerization part of your treatment mode is. So that's also a good study there. But now we're going to move on to the next topic on how to rectify and or to maintain good polymerization. Now, I'm going to ask you a quick question again. Lastly, this is one last poll. I'd like to know, how long do you spend curing each layer of your composite or the composite that you guys use? So I'm just going to launch that. Let me know what you think. It'd be nice to know how everyone is practicing in their clinic. Okay, right, thanks for taking part, everyone. So just going to launch that. Let's see if it comes through. Yeah, great. Okay, so majority of you guys, so 3/4 of you guys spend 20 seconds curing each layer. Okay, and some of you are still spending 40 seconds. I'm assuming those are the guys who are using the halogen lights, and some of you guys are using only need 10 seconds. Great, okay. Now, I'm just going to show you now the next part. So there was a survey done very similar to what I just did there, but on a broader spectrum, where in Norway, they actually asked dentists how long they spent curing each layer. And they said on average was about 28 seconds. Another study done in Germany, and they spent 20 seconds. Just imagine now, we're talking 20 seconds per layer, okay? So that's how long it takes. Now, with the current guideline from Ivoclar Vivadent's products, so with the stages that they have, so you have the adhesive universal. So this is the adhesive that you apply. Once you apply it, you only need 10 seconds. With the bulk fill, whether it be the flowable or the moldable one, okay, for each up to 4 millimeters, you only need 10 seconds. And that makes life a lot easier, because if you look at the conventional way of dealing with things, they actually spend 15 to 30 seconds or 10 to 20 seconds per layer, or 10 seconds per layer. And when you have a bulk fill material, for example, you can really cut down the time, especially in the posterior region or in the maxilla region as well. As long as, patients, it's more of a pride thing if you're doing layering technique. I'm not saying don't do layering technique, but if you want to be quite efficient but still provide pretty decent aesthetics, it's not a bad idea to have a system where you can actually just be quite quick with each step and not compromising on quality, okay? But now with the super fast bulk fill, nowadays you can cure composites within 3 seconds with the Tetric Power Fill and Power Flow. Now, it all depends on what you have, because if you got a light cure that's able to produce about 3,000, so we're talking between 2,700 to 3,300 milliwatts per centimeter squared, you can cure each step, the adhesive, the flowable bulk fill, and the moldable bulk fill within 3 seconds, okay? However, otherwise, if you've got a normal light cure that produces about 1,000, you can still do it, but not in 3 seconds, but you'll need 10 seconds, okay? So that's not an issue. But yeah, now you know that you can actually cure and make life a little bit quicker in the clinic. Right, so 3 is the magic number there. And what they found, so from a study that we did a little competition here in Shan where we invited 34 different dentists from across the globe who do composites there. And what we did is we split the teams into 2. We put one into a conventional layering technique and then one in the bulk fill. So, you know, like that table I showed you. So we put them into those 2 groups and then we timed them. And what they found on average from the group that actually did all the bulk fill with the 3-second curing, with the power cure, they actually saved 57% of time in comparison to the conventional layering technique. And that was the difference that they found. And how is that done? Because of ivoclar. So ivoclar is a photoinitiator that is 10 times more reactive than camphorquinone, so you can cure faster and deeper into the composite. That's why we are able to cure for 3 seconds up to 4 millimeters depth. Okay, so it stands here with the rest of the other photoinitiators, and they also have a spectrum of about 370 to about 460. So if you do have a blue phase light cure, it won't be a problem, obviously. But if you do have other light cures, I think majority of the light cures in the market will be able to initiate the polymerization with composites that have ivoclar. Okay. The great thing about the ivoclar also is that it is very yellow in color, but unlike camphorquinone, it actually loses its color. So you can use it for anterior direct composites or anterior composites in general, or if you're doing a veneer case, don't be concerned when you're applying it. It's going to be yellow, but once it's cured, it disappears. And so this is the comparison between the standard monomer with camphorquinone, and then this is the demonstration with the ivoclar, and you can see how quickly it initiates the light in fraction of a second. All right. Where does that stand? So you got ivoclar, which is marked as red here, and it will be initiated by the polywave as well. Okay. Right. With the Essensio technology, a lot of the times when people are talking about wanting to cure bulk fill composites, they think that all composites need to be very translucent, and they have, yeah, of course they need to be translucent so the light can pass through, because if it's too opaque, then of course you're not going to get that energy down to the base of the composite, especially with the bulk fill, you know, when you're talking about 4 millimeters. So with the tetric power flow and power fill, they are initially translucent, as you can see here, but after polymerization, they opacify and become, and then they lose that translucency and they go down to about 10% here. So that's why we recommend using power flow as a dentin replacement part, and then you use your power fill, which is the moldable part, on top, and that has a higher translucency compared to the power flow, so that you can mask the aesthetics. You can mimic the aesthetics. So it's a bit like dentin enamel. Okay. And so here's a case done by one of our colleagues in the R&D department, where she replaced this insufficient composite here, and she replaced it with the bulk fill material. So she actually used tetric power flow and power fill, and looks pretty decent for an immediate result, after removing. As you can imagine, the tooth is also a little bit dehydrated too. Okay, now you're thinking, okay, how do I know that I'm producing enough energy and depth? So we're talking about, in this case, they use a blue face style. This is one way of checking if you're getting enough energy up to 4 millimeters. You can cure down your syringe for about 10 seconds, and then you extrude out the material that's actually hardened, and then you remove it, and then you can measure it and see the depth. And here they found 6.4 millimeter here. But of course, that's material wastage, right? So another way of actually doing it is by actually using a radiometer here. And this one is the blue phase meter, and it actually measures the intensity of your light, which you can also purchase here. And how does it work? So you've got the blue phase meter here. If you turn it over, you just need to measure the light guide. Remember, because the light guide thickness determines the intensity. You input that in to the blue phase meter, and then you light cure it, and it should read the intensity for you. And that's how you'll know if it's producing the sufficient amount. But it's very important, a little tip, not to tilt your light guide, because if there's any light escaped, you're going to get a false reading. So make sure you've either have it completely flat, or you use your finger to fixate it so that you're not having any loss of energy there or intensity. What's also quite useful is to have a light guide that's actually shortened, because like a toothbrush, if you can also use it on your pediatric patients as well, or people who have struggled to open their mouth wider. So make sure you have a light probe that's wide enough and also short enough as well. And what we also found is that the light transmission is an issue as well. So when you've got a light probe that actually has the LED at the tip, you're going to have more scattering of the light. And when there's more scattering of the light, the intensity is lost at where it's trying to be received. So it's better to have a light probe that's actually, so there's an optical fibers in these light probes, and they actually generate that's how you get that homogeneous light distribution. And it's not going to have much of a scatter. And the same thing with the turbo light probe. This is used for if you want to pre-cure quickly for your veneer fits. So if you're placing a veneer, you just do a turbo light just to fixate it, remove your excess, and then fully cure it. And there are light probes that do have like a glass opening here. Some of the intensity is lost around during the travel there. So that's why it's quite good to have one that's actually all darkened out, so that it doesn't lose any energy or intensity until it's delivered at the tip of the light probe. Okay, and that's how you get the beam homogeneity. Now, here we have the lithium disilicate, and you have the zirconium oxide restoration. They look very similar in appearance from the outside, okay, because they've been, so the zirconium oxide has been veneered, okay, to mimic the lithium disilicate. But if we shine the light through it, you can see how much light can kind of pass through the lithium disilicate, but majority of it is lost in the zirconium oxide, yeah? And if we put this onto a graph, for example, with the lithium disilicate or lucite reinforced, which is even more translucent in comparison, and compare that with the oxide ceramic, you can see that not so much, you can see how much translucency are in each of these materials. So because now we're moving on to the indirect restorations. And there was an internal study done where we shown normal light at high power mode, so we're talking about 1,200 milliwatts per centimeter squared, and we put IPS Empress, which is one of our most translucent materials, and we compared that with the low translucent Emax press and a high opacity, which is mimicking the zirconium oxide. Okay, we do have zirconium oxide, but this is comparable, I mean, in terms of translucency. And as you can see, after 1 millimeter of ceramic thickness, it's only the IPS Empress that's probably still receiving the minimum requirement of 400 milliwatts per centimeter squared. Okay, when we're talking about Emax Press, low translucency or high opacity, yeah, you're not getting enough intensity, you're not getting enough energy to cure under that ceramic. So then 2 millimeters in, after 2 millimeters, even with the Empress, you're not getting enough as well either. So just imagine, and this is just 1 millimeter, and we're not talking about flat surfaces here. When you're getting your restoration, you're going to get some bulbosity. Your technician's going to make it nice and round and so on. And you're going to cure through the more than 1 millimeter. So you need to think about that too. And there was another study, a master's thesis done in 2015 that showed the influence of not just the thickness, but also the translucency of the material. And then what they found, and this one actually compared some zirconium materials and with Emax CAD. Yeah, that's a lithium disilicate material. Whatever it is, they all had the same result. They all lost intensity, whether it be because it's because of the translucency of the material, or whether because the thickness of the material reduced the transmission of the light. So as you can see, with Emax CAD being the most translucent, then you've got, like for example, Ruxia, which is really opaque, and you're not getting that intensity. And then as you can see, even from 1 millimeter, you're losing a lot of the requirement. So going back to here, as I said, you wouldn't be also sure that you're light curing appropriately. Okay, so how do we do that? With the Blue Phase Power Cure, it has also a curing assistant. And what that means is what we call the Polyvision. Now, just imagine you're curing for 3 seconds. That's a very short period, and if you lose 1 second of intensity, so just imagine you're light curing the restoration, but you're not concentrating for 1 of the seconds. That's 33% of energy lost that you could do with to cure your composite, especially with bulk fill, because you can't really take the material out and check that it's hard enough. So every second is crucial. So hence why they came up with the Polyvision, to be sure that you're not inappropriately curing. So like with the new cars nowadays, you have this lane assist, lane keeping assist. So when you veer off from the tooth or the material, the light cure will vibrate and bleep. Now, if you were to do the same thing with like an emergency brake, but you completely miss the tooth, for example, or even accidentally try to light cure someone's eye, for example, it won't switch on. It will just cut off completely. Okay, so you can be sure of that. Now, how does it work? Well, so when you shine the light, there is a sensor here that actually gets a feedback from the white light that it's shining onto, and then it will sense it. And then there is a certain intensity that it needs to pick up. And if it goes below a certain threshold, it will know, okay, it's actually not being light cured appropriately. And if it's completely off, then it won't switch on. Okay. And so they did this test done. And yeah, as I mentioned, if you're angling it or pulling away, it can affect the intensity. And then they checked the Vickers hardness test. So they checked the depth of, they checked the hardness at each depth once they spliced it. And what they found is that they were, you need about 80% of Vickers hardness, and whether so with this with the light cure, even when it's angled or there was a lot of distance, they were still able to get sufficient hardness on the composite. The only time when it didn't reach the minimum requirement was actually when the light probe was covered with composite. It actually reached just over 70%, but not enough for the minimum requirement of 80%. So that's another thing you need to be sure of, is that your light probe is clean. So make sure that you You clean the light probe. Don't allow any composite to actually block any of the energy passing through. Make sure that you use a nice sleeve. So at least with the blue phases, they have their corresponding sleeves. Use a shield to protect your eyes and the patient's eyes as well for themselves, and cleaning the probe. Okay, so here's a quick overview. Just be aware of what generation LED you're using, whether it be a second generation, third generation, fourth generation. You know, nowadays, at least the minimum requirement would be a third generation nowadays, because at least you're able to use any composites on the market. But of course, if you want the benefit of being able to know that you want to cure accurately for 3 seconds or even 10 seconds, then yeah, you can upgrade to a fourth generation. Now, just going to quickly touch on the pulp temperature, which I talked to you about, because you know you don't want to be curing multiple times on the tooth, because it can increase the pulp temperature. And what they found was that actually they didn't find any inflammatory changes even at temperature of about 11.2, but another study actually said to be on the safe side that you should half it and actually not allow more than 5.5 degrees Celsius. Okay, and here, as you can see in some of the light cures in the market, quite a few of them actually do raise it beyond the 5.5 threshold. But with the blue face style, which is the previous range, went up to about 4.9 degrees Celsius. But how does it compare with the blue face power cure? Because that produces 3,000 milliwatts per centimeter squared. So it's a lot more powerful. So there was a study done in Brazil, which is quite extreme, but actually, you know, it's quite useful to demonstrate. But what they've done is they elected a few patients who were going to have orthodontic treatment, and they were going to have some elective premolars extracted. Okay, and before they did that, they used those premolars to expose the pulp right the way in order to insert a thermocouple, and then they sealed it. Then, on an extreme level, they actually made a class 5 preparation on the buccal surface of the premolar that they were removing, and then they light cured it with the blue face power cure, and then they also used the standard blue phase style or blue phase 20 with this high power mode in comparison, just to have a control test, just to see how much of what the temperature increase was in the pulp. So this is obviously in extreme cases, and we don't recommend light curing on the buccal surface. It's not indicated. Only curing from the occlusal surface. That's the current guideline. But here, in this case, they did it on an extreme case. And what they've done here with the blue face 20i, so this is in the high power mode, so about 1,000 milliwatts per centimeter squared. And when they cured it for 10 seconds, it increased it to almost 2.4 degrees Celsius. And then when they cured it twice, it was about 4 degrees. Okay. With the 3S power cure, so this is at triple the intensity, and it increased it to a similar level of about 2.4, 2.5 degrees Celsius. And when they cured it twice, it was still under the threshold, so just under 5 degrees Celsius. So it was still acceptable. However, with the blue face power cure, you cannot cure for more than two times on the 3S power cure mode. It will actually allow you to buffer for a period, so you won't be able to turn it on again for another 20 seconds till everything cools down a bit. So that's just the safety net that we have. All right, now a quick summary. So make sure that your light probe or light cure has the right amount of intensity. Make sure that you have the emission spectrum that's wide enough to kill any composites in the market. Make sure you know your exposure times. So, you know, depending on what composites they are, you know, you need to be sure that you're curing sufficiently. Make sure that when you're actually using the light probe, that you're actually positioning it and stabilizing it and concentrating the light on the tooth or the material that you're trying to light cure. Make sure you maintain it, so check the battery life, make sure that they're always charged, make sure that the light guide is clean, that the light guide is producing a homogeneous or distributing a homogeneous light, and that you're producing the right amount of power output. And of course, safety first, always have a shield or a glass to protect everyone's eyes that are involved in the room, okay? So please don't let the light curing stage to let you down in your composite restoration or your indirect restoration technique, all right? I hope that was helpful. There are many other webinars that we are offering, of course, every week for dentists and dental technicians, and also for our dental hygienists, colleagues and therapists. You're more than welcome to join more webinars that are going to be on this website at ivoclarvivadent.com/academy, or if you've got a smartphone, you can just scan the QR code that should take you directly to the website. All right. Okay, so we've come to the end, and I really appreciate that you all joined me today, and I hope at some point that we all meet each other at some point in the future, so we can discuss things in person. And but otherwise, in the meantime, you know, join our webinars, and maybe in the future you can join us in Shan, or I will come to your countries and we can do a session together. But until then, keep safe. Work smart, not hard, and we'll see each other soon. Take care. Bye now.